indeed, I'm going to try and talk about how we integrate quantum computing with HPC and what the challenges are. I won't talk much about AI, but I can talk a little more about it if maybe over dinner, we'll see. I'll come back to some of those. Always acknowledge your funders first in case you don't get to the last slide where you've got them on. But a lot of UKRI funding has gone into this to get us to this point, and I'll have more about that towards the end. So the question is, are we going to have useful quantum computing soon? It's a pretty exciting time. There's an awful lot of hype out there. Big companies, they're making big claims. There's startups that are growing. There's spin-out companies from academics, theorists and experimentalists. And what you don't have to forget about this is there is 30 plus years of hard work to get to today, okay? The first stuff was late 90s. So this is not an overnight sensation. It's just you didn't hear about it earlier because it wasn't ready yet. That picture, so I've put one up from 2017, but I'll tell you why I like that picture. You can see the qubits on it with your naked eye. That's a standard size chip, that picture, like this size. And the qubits, if I go and point them out, I have to get back to the microphone to tell you. So the squiggly things are the resonators that control them and couple them. And the little squares are actually the superconducting circuits that are the actual qubits. Now, question for the audience. I know some of you are old enough to remember when we could see a classical bit. Anybody? Yeah, some hands going up. Shout out a year or a decade. Got it. That's about when core memory went out. Okay, if you don't know what that is or was, go and Google core memory. But you could actually see the little copper circles what were the memory for the bits in up to 1975. Okay, so that's where we are or were in quantum computing about a decade ago. Okay, just to get some context and some perspective on what's going on. So now we're up to about maybe 1,000 now that IBM are claiming to have. How noisy they are is another question, but we'll get to that. Right. So now we've got kind of a sense for where we are on the journey. What can they actually do? Okay. So the claims that have been out there of supremacy or whatever they want it to be is that with about 1,000 qubits of like the ones just a little smaller than the ones in that picture, and they're noisy, they're imperfect, cooled to very low temperatures, big cryo. For a particular random sampling task, which is not useful, it took near exascale HPC to verify that the output was indeed quantum. And of course, then there are lots of arguments about this because people went, well, we didn't know you wanted an algorithm to do that. I can make it much faster if you want. But the take-home message from the hype is that there's real potential there if we can use it for something we actually want to do. So it's time to think seriously about how we could use it for something that is not just making a headline. So there's my overview. We've done the hype. I'll do some motivation and some context for current computing. Probably very familiar to this audience, but it's good to, again, have the context. I'll go through a certain amount of basics of what is quantum computing. And for a lot of you, this may be all you need to know at this stage, enough underneath the hype that you have an idea of when you need to be seriously interacting with it. Then I'll talk about useful quantum algorithms and some of the projects to look how to develop those. And as we go through, there'll be a to-do list for what it might take to integrate HPC and quantum. So we'll start. Okay. Useful quantum computers will need to be doing something we can't do with what we already have, or doing it much better. So we better look at what we're currently using the big machines for. That's the top, the top 500 picture. And there's a list down there. I think that picture's Titan, actually, from where I got a data center from. But we have molecular dynamics, simulating biomolecules and things like this. Modeling pandemics, that turned out to be quite handy, actually, quite recently. Simulating the whole human body, either an individual or generically. Quantum materials design, so material simulations. Weather and climate forecasting, that's pretty important across the board in economic and social settings. Nuclear explosion simulations, lots of fluid simulations, again for design and engineering, as well as the climate modeling, and a whole lot of things they don't tell you about in detail. But that's the molecular and materials simulations and the fluid simulations together make up a big chunk of the use of Archer 2, for example. And then this stuff uses megawatts of power, right? We've had power mentioned already. If we want substantially more computing, we definitely need a plan B, whether that's quantum or not, right? So we know what happened to silicon chips, right? We can't cool them any faster. And I had the cooling picture on the previous slide for a reason. So we've still got the feature size going down. So what we've got plotted here is the number of components on a chip, the speed in hertz, and then the red line coming down is the feature size. And then it stops being possible to plot the thing up in that circle at the top because you just have a plethora of different types of chip for different purposes. And it stops getting any faster. And it stops getting faster just for the basic physics is that the heat conductivity of silicon means you can't cool it as fast as you're producing the heat in it. So you'd melt it. Simple as that. But you're already diversifying here, even within silicon, to optimize it for the applications. And then we're diversifying beyond silicon. This is a bunch of stuff that is much more the fun research side of things rather than serious stuff at this stage. But yes, we've got lots of different types of processors that people are trying out to see if they're going to be useful, lower energy, better compute model out of them. And that's nice. They almost all have a conventional computer of some sort as the control layer for them. So their hybrid is the norm and some form for computer architecture. In practice, we have all sorts of co-processors handing off jobs. Even the network card will have a chip on it to do a lot of local processing. And the unconventional ones do too. Quantum, coherent icing machines, reservoir computers, the slime mold I had on the other picture. So that's the norm, but that's actually not what our theory of computing is normally about. We've got single paradigm models. So we've got Turing machines for classical. Nobody builds a Turing machine. It's not possible because it's got an infinite tape, right? So you get quite close for some, but and then you've got an analog for Shannon's GPAC model, again, very abstract. There are lots of quantum models, by the way. You've got a gate model, a quantum Turing machine, measurement-based quantum computing, quantum annealing, and topological quantum computing, which you hear about occasionally from Microsoft. Not that anyone's managed to make one of those yet. And there's stuff in between. So the linear optics of what you can do with photons can give you an intermediate power sort of computing. So one of the first things we need is to actually have good models of hybrid computing. And that's not just for quantum. It's pretty hard to do the CPU, GPU stuff in an optimal way. There's in terms of actually having the theory that will support what's being done in practice. In practice, it's quite experimental to get that to work and to really use the hardware in the most efficient way. So if we work on that, that's going to benefit across the board where computing is going at this point, not just to bring quantum into the mix. Right, so if we're going to talk about what quantum computing is, let's make sure we've got a good picture of what we mean by computing. And I put slime molds up there, for example, which most people wouldn't consider as something you'd compute with. I can fit it into this picture, but that would be too much of a diversion right now. So this is a slide from my public outreach talk where I've got pretty pictures on it, but the reference at the bottom is the serious work on this without the pretty pictures in it. And it relates science, engineering, technology, and where computing fits into that as a process. And pretty much you end up with a flow like this, where you've got a problem. So some entity, here we've got the user on the laptop, and you need to translate that into something that a computer can understand, actually put it into the hardware. Then you run the program, you get a state change at that point. Because if you didn't change something, if something didn't evolve, I could replace the bottom bit with a brick and nothing would change, right? So you have a state change, so your output is something different in that sense. Then you have to do the decode process and match it back to your original problem. So that's our picture of computing. And I'll come back to that in a couple of slides so we can see exactly how quantum fits that and where the quantum bit and the classical bits fit together at first pass. So quantum information processing is built on the idea that quantum logic is different from classical logic and it allows greater efficiency. And there are actually many sorts of logic. So spiking neural nets are a different kind of logic too, and they compute differently. So this is the table lining them up. So you've got bits or you've got qubits, and the bits are just 0 or 1, kind of end of story. You don't have something halfway in between. In quantum, you do, and it's done coherently where the alpha and the beta are complex numbers, or to put it another way, that plus sign between alpha and beta could also be minus, and that's different. Okay, so that's a wave-like property that qubits have. Then in classical, you have yes or no. You have binary decisions to correspond with the 0, 1 of your bits. But in quantum, you get yes and no in superposition. So you can do both options at once. In classical, you have to add random numbers. They don't come for free. You either have to generate them pseudo-random or go and get some randomness out of the environment and stick it into your computation if you need it. In quantum, the measurement outcomes can be random. In principle, is purely random, exactly random. It's part of the theory that says they're built in. So the computation is going to be different if the logic's different. That makes sense. The question then is how different? So computability, so what you can compute, is the same. You can simulate a quantum system, just not necessarily efficiently. But the complexity, so how efficiently, can be different. And then it depends on your definition of efficient, right? So the theorists take that as scaling polynomially in the size of your problem or the size of your system. But in practice, what we need are answers on humans' timescales. And square root of the age of the universe is still too big, right? Very roughly speaking, and don't think there's anybody in the room to challenge me on this, but I'm quite happy to be challenged. The quadratic speed up exploits that quantum coherence. So the wave properties, the fact that you get a sign between the 0 and 1 components, and you get interference therefore. But the exponential speed up exploits the superposition and the fact that that scales up exponentially in the number of qubits. But what we need to do is compare real physical devices, not mathematical theories. They give you a guide, but that's not the end of the story at all. Right, so let's explain a little more about how it works in a couple more slides. So here we've got our numbers from 0 to 7, and then our binary version of it. And we want to compute a function of those x for those 8 different values of x. So classically, you would run the program 8 times, once each. To do it in parallel, sure, but that's still 8 times. If you can do them all at once, and quantum mechanics lets you do this in superposition, then you only have to run it once on one set of 3 qubits. But there is no free lunch. You get a superposition of all 8 answers, right? And if that isn't what you wanted, you still haven't got anywhere. So you need to select one, the one that you want. And if you can do that, then you can get a quantum advantage out of this. So how do you do that? You need smart algorithms to do that. So useful quantum computing needs the quantum algorithms. That's what's going to unlock the power of the thing, that theoretical power. If you can't make an algorithm do end-to-end what you want out of it, it won't give you a useful, excuse me, speed up. Right, so I promised that diagram would come back, the one I had on the public outreach pretty slide of what computing is. So there it is flattened out. We've got our input problem. We've got to encode it into our quantum system. Then that's written in those funny brackets to be a quantum system. So the bit with the green background is the quantum bit. We then do the time evolution, which is the U operator on it. And then we get a different state as our output, which we can measure or decode and get our result. So that corresponds to what we think a computer should be doing in cartoon form. And that U is unitary or open system dynamics according to quantum mechanics, according to what physics tells us we can do. So we can do a sequence of quantum gates, or we can engineer a Hamiltonian and just evolve it continuously in time. And actually that picture is most of quantum information processing. If you're doing communications, your goal is to have the input and output match, and what happens in between on the transmission line or whatever doesn't disrupt it and put errors in there. And just as a little aside, another sort of condition that identifies information processing very often is that the encode has got arbitrary choices in it. So one way to recognize that it's not just a physical process is that you've made some arbitrary choice for what's your 0 and your 1 in here. We could do spin down or spin up, and in principle, it makes no difference, provided you do your encode and decode consistently. Now, in practice, of course, it does, because the 0 and 1 may well have different energies, but then you can use that to randomize your assignment of what the 0 and 1 is, and that will average out some of the errors that come from the way the device operates. So yeah, but it's that arbitrariness is a signature that you're doing information processing, that you've actually encoded something into what the physical system you're using to represent it. Quantum gates, right, busy slide, but a lot of this is, you can see in the middle, I've got the exact same diagram of what we're running, and I want to see what I can do with the U for how do I program it. The qubits are two-state quantum systems, many ways to encode them in actual physical entities like electrons or photons, but we localize them. They're distinguishable. So we don't have the funny quantum statistics of identical particles going on here, because we can tell each one apart because we know where it is. Or what you need to know for this, what you need for this program, it's got to be able to be efficiently specified. Now, if you're thinking of it as a matrix, if you were simulating it, you'd need 2 to the n by 2 to the n for the size of your matrix operator. So you've got 2 to the n possible states, and then the size of the matrix that's operating on that is the square of that. That's not efficient. So you're going to need a sparse matrix, effectively, a description that corresponds to a sparse matrix for what this is. And you will also need to be able to decompose it into elementary operations. And like classical, you can build everything out of a small number of elementary operations, 1 and 2 qubit operations. So if that wasn't possible, we would be trying to build quantum computers very differently than the way we're actually doing them. But it's an equivalent result to what you have with classical. Which set you choose depends on your hardware. That's really lower level than most people, you don't worry about what voltage your bits are inside the chip these days. Well, there are a whole bunch of physicists worrying about that level of stuff. Right, let me try and go through. I will probably